Lecture 13, example of Stokes Theorem via exterior algebra. Now set up, let vector field F given by x, y, and z. The components are F1 is minus y, F2 is x, and F3 is 0. The surface S is the unit disk in xy plane. x2 plus y2 is less or equal to 1. Orientation, upward normal. You see there's a unit vector k. So this boundary of S is traversed counterclockwise, you see. Now, step 1, let's mark here. Convert F to one form omega, okay? So F, x, y, and z, minus y, x, and 0. This is converted, omega is minus y dx plus x dy. Now, this is to convert, I just take the dot product in classical mechanical vector calculus. There's a dot product between f and dr. You see, it leads to the same in this case on the exterior algebra. This is f1, this is f2. f3 is 0, so minus y dx plus x dy. Now let's compute the two form d omega. Okay, d omega is d, this is omega over here, okay? You just expand, you see, because the differential in this case of minus y is minus dy. So this is minus dy wedge dx. Now, in this case, the differential of x is dx plus dx wedge dy. But minus dy wedge dx is plus dx wedge dy. So this d omega leads to 2 times dx wedge dy. It's quite straightforward. Now, this is step 2. Now, step 3. Compute the integral on the surface of d omega. This is a two form. We integrate of the unit disk as xy belongs to R2, x2 plus xy, x squared plus y squared is less than or equal to 1. Now let's derive this integral here. So it's 2 times dx dy. I just substitute, okay? This is d omega just over here, you see? So let's switch to the polar coordinates. X is r sine theta, y is r cosine theta, and dx dy is r dr d theta. Now dx dy, you see, I switched to the polar coordinates, is r dr, in this case, d theta. This is element of area, okay? This area element in cylindrical coordinates in this case. In this case, the disk. So this integral 0 to pi on theta is 2 pi. And this is I squared divided by 2. From 0 to 1, it is 1/2. So this integral here will be pi. Thus, integral of the omega is 2 pi. Don't forget this 2 is over here, you see? So it's 2 times pi. Now, step 4, just to verify the Stokes Theorem. Let's develop the integral on the surface of S of omega. You just substitute omega, okay, right here. The attention now, x is r cosine theta, but the disk has a unit radius, so this is cosine of theta. Likewise, y is r sine theta, so this will be sine theta, since r is the unit radius. Now theta varies from 0 to 2 pi. Now dx, okay, is minus sine theta because this is cosine. Okay, the differential of cosine is minus sine d theta. Likewise, the differential of sine is cosine d theta. I just substitute, okay, this in omega. Okay, this is one form. Attention, omega is one form. D omega is two form. You see? Now let's substitute quite easy. Minus minus plus sine square plus 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 cosine square. This is 1. So the omega, the result is equal to d theta. Now I integrate. You see? Don't forget the 2 over here. You see? This is omega is 2 times, okay, the area element. So in this case, this integral just substitute d theta here is 2 pi. Now conclusion, you see, this is 2 pi and this is 2 pi. Conclusion, both integrals agree. So this Stokes theorem is verified. That's a simple example just for you to grasp the importance of the Stokes theorem. Okay, in this case, in the exterior algebra, okay, that's the bridge between exterior algebra and the vector calculus. That's it.